Alloy steels are made when iron alloy is alloyed with other transition metals such as cobalt and chromium. An alloy is basically a material that's made from a mixture of metals and carbon, sometimes. Which row of the table shows the typical properties of a transition metal? So transition metal, if you remember, is any metal that is found in this middle block of the periodic table, and they have certain properties in common, and most of these properties you just associate with normal metals anyway. So for example, they have a high density, metals have a high density, but what you do need to know about transition metals are two things. They can be used as a catalyst to speed up industrial reactions, and also that's unique, you need to learn that. And the other thing is they can form coloured compounds, whereas non-transition metals form generally white or colourless compounds. So for example, copper produces blue compounds, lead, yellow compounds, and so on. Figure 1 shows the chain on a bicycle. Explain how lubricating the chain with oil prevents corrosion of the steel chain. So, corrosion is obviously when when water and oxygen get to the iron and cause rust. So oxygen and water are needed for the chain to rust, and we know that oil prevents or doesn't mix with water. So oil acts as a barrier to oxygen and water. Iron fences can be galvanized by coating them with a layer of zinc, so that's a protection method. When the layer of zinc is scratched, exposing the iron to the weather, the iron does not rust. Explain why the exposed iron does not rust. Well, zinc is more reactive than iron, so it will basically bond with oxygen ahead of iron. It's what we call a sacrificial metal. They're used in ships, ship hulls all the time, because obviously water can corrode metals, so you protect it with something more reactive than the valuable steel that makes the ship. So zinc is a sacrificial metal, you need to know that term. It will sacrifice itself to protect the iron. It reacts more easily with water and oxygen than iron. Metals have high melting points. Explain in terms of their structure and bonding why metals have high melting points. Well, if you look at metals, you have basically a lattice of cations or positively charged nuclei, and in metals you basically have delocalized electrons. So the electrons, unlike in non-metals where they orbit in the shells and they're restricted to those shells, here they can actually move in between the lattice structure throughout it, and that's why metals conduct electricity. And also they're negatively charged, so they're very strong forces of attraction, or electrostatic forces of attraction. That's just a force of attraction between particles of opposite charge, between the cations or the positively charged nuclei and the electrons. So that's how they're bonded, and that's the structure described. And the electrostatic force of attraction, the strong electrostatic force of attraction, explains why they have high melting points, because you need a lot of energy to overcome that electrostatic force of attraction. So cations are surrounded by delocalized electrons. That describes the structure. And you explain why they have a high melting point by saying strong electrostatic forces of attraction between them. That's why anything has a high melting point, because of strong electrostatic forces. So always include that in any question about high melting points. And if it's low melting points, then you must talk about weak intermolecular forces instead. But you wouldn't talk about low melting points with a metal, or they wouldn't ask you about mercury, between a metal or a giant ionic lattice or ionic compound or a giant covalent structure. So you need a lot of energy to break those bonds. Stronger electrostatic forces of attraction between them. So you need a lot of energy to break those bonds.